Okay, so here we were. Last time we were talking about Green's theorem. I'm going to do an ultra quick rehash of what we talked about last time, developing up to where we didn't quite get to the statement of the theorem. But the very first thing we talked about is boundary. Remember, going forward, this is a loaded word. The word boundary no longer just means, where the fence is around your property, or, the dividing line between set and not set. Now, furthermore, the word boundary means an orientation. It means with a specific, arbitrary to be fair, but conventional standard, and therefore to be always understood orientation. And the rule about the orientation is, as we discussed before, and again, details we talked about last time. Okay, but we talked about this oriented boundary concept. Next thing we talked about, this idea of accumulation. Hardly was worth talking about before this point, because everything that we encountered, by design, in some sense, the whole concept of a Riemann sum, aka double integral, triple integral, is that it is something that you use when the whole is the sum of the parts, where you can take a question, chop it up into little pieces, and add up the answer that you get on the little pieces, right? So every application to which we applied an integral, be it in a single variable calculus class or double integrals or triple integrals in this class, they are all accumulating quantities. And the reason I talk about this here is because we encounter a new accumulating quantity that doesn't seem at a glance like it ought to be, right? So the fact that boundary circulation accumulates is not only, I would say not only unexpected, but it's counterintuitive, right? And so in order to be able to talk about the counterintuitive, but then the fact that it is, I need to be able to talk about what it is that I'm talking about, thus the word accumulation. Okay, again, all this means is that the whole is the sum of the parts. And I'll remind you, this is ultimately, deep down, this is the core, the nugget of why does Green's theorem work. It's the fact that boundary circulation is an accumulating quantity. Okay. All right. And then we made some discussions about how, in fact, any accumulating quantity you can think of as being distributed over the interior, whether it is physically or otherwise, right? And I'm going to have some more things to say about that later. Oh gosh, when we get to that today, the coin flip, we might or might not get to the further discussion of that today. But I want us to think about boundary circulation in particular. Like all other accumulating quantities, I want to think of them as being distributed over the area, even though we actually compute them on the boundary. That's a distraction, that's a red herring. What we're really interested in is the fact that they accumulate over area. Therefore, I want to think of it as a quantity that's distributed over area. Okay. Lastly, we talked about the resulting corresponding notion of density. Mass is distributed over area, and so you can talk about how much over what size. Mass per unit area, mass density, right? Extremely routine concept. Just to be clear, by the way, we call it mass density because mass is the quantity in question, whose density we're describing. Said differently, mass is the numerator. Right? Well, okay, if we're going to do that, then we can do the likewise by analogy with any other accumulating quantity. We've already done so for stuff like population density, right? Same idea. And so likewise, we're going to talk about circulation density as what you get when you look at circulation per unit area. Again, the prefix circulation for circulation density from the fact that circulation is the quantity, circulation is in that numerator. Okay. All right. And this is where we left off last time. We were almost right up to being able to state Green's theorem. So that's what we're going to start with today. And here we go. I claim that everything that we've got here on this screen is stuff we've really already established. We've already got all the pieces. We just kind of have to put it together to get our big result. Here it is. First, circulation as a concept. Sure, it's defined as an integral, but I want to think of it as a thing. I want to think of it as a stuff, kind of like mass, kind of like population. It's a quantity that's represented by a letter. And don't think about how to compute it. How to compute it is a distraction here. Right? Think of boundary circulation as being a kind of a stuff. Okay, next observation. We talked about the fact that it is an accumulating quantity, and therefore the whole is the sum of the parts. And like every other accumulating quantity we've ever talked about in this class or previous, you can therefore write it as an integral, right? A Riemann sum. Chop it up, add it up, take your favorite perspective on that. And then, wait a second, now let's look at this d sigma thing, and let's remind ourselves that we've already involved that in an equation. D sigma we've written as circulation density times area. Right? In some sense, the streamlining of this statement, you would say circulation density means circulation per unit area. And so said differently, circulation density is what you multiply by area to get circulation. And Green's operator is just another name for that circulation density. So again, now what I've done here in this discussion here is just really a restatement of ideas we've already talked about prior to this screen. And notice though that we get this really unexpected result, and that is that a boundary line integral, aka a boundary circulation, can be computed as a double integral over the interior, the thing whose boundary you're talking about. Double integral, that is, of the, then again, say it however you like, Green's operator, circulation density, dq dx minus dp dy. There's lots of different ways to say circulation density. But circulation is an integral of circulation density. But more interesting, more of an eyebrow raiser, when you say it as a line integral, can be computed with a double integral. How are we doing? I want to pause here, make sure everybody's okay with what we're doing so far. We've got examples lined up momentarily here. All right. Let's do those examples. Okay, so the question here says we want to compute a line integral. Curve is given, vector field is given, compute the line integral. And we know how to compute line integrals, a couple of different ways to compute line integrals. Now I want to make an insightful observation here though before I get started, and FYI, expect to need to do the following yourselves, right? The questions will not always announce the solutions in the statement of the question, right? And this one specifically also did not. Notice the word circulation not present in the statement of the question here, right? And so there's no sort of like tip-off that you should be thinking Green's theorem. The tip-off comes from looking at the curve. The curve being a circle. You can notice for yourselves that circle is I'm going to kind of commit a little math crime here, forgive me. It's a boundary, right? And as soon as you notice that it's a boundary, you're thinking, hey, this I know a theorem about computing line integrals on boundaries. So now let me confess to the math crime. I say this is a boundary, but in fact, technically, it's not, because look at that clockwise, right? This says a clockwise oriented unit circle, and clockwise is not the deal with boundaries, right? We have very specific rules. You're going to say the word boundary, that means oriented according to a certain convention, and this is not it. So, and by the way, this is a big deal. I mean, you look at the statement of Green's theorem here. Green's theorem says, again, that you can compute this line integral with this double integral, but specifically only for a boundary. Oh, golly, what was that? I mean, okay, specifically only for a boundary. Very importantly, Green's theorem does not say you can compute any old line integral with a double integral. It doesn't say that. It only, very narrowly says if you have a boundary. as your curve. So to get, again, particular and upset about this, we do not. We have a clockwise oriented curve. So we can fix this though, and the big idea is to observe that, C minus, same curve opposite orientation, C minus is a boundary. I mean, absolutely, right? No problem. It's not the curve we're interested in, of course, but C minus is a boundary. Specifically, C minus is the boundary of this unit disk. Like that. This is a curve to which I can apply Green's theorem. And so let's do that. Of course, I need to recognize why I'm interested in the curve C minus. The reason I'm interested in the curve C minus is because C minus and C are very closely related curves. We get the minus sign on the evaluation there because, of course, that's what you get when you evaluate with the wrong orientation, right? With the opposite orientation. So you can trade C for C minus, but you have to pay for it. The price is that extra minus sign. Okay. So, C minus. I like this curve C minus. I've got my answer written already now in terms of C minus. The reason I like the curve C minus is because it is a boundary. So let's recognize that. Right? The whole point to rewriting in terms of C minus is because C minus is a boundary. And once I have that noted, here's where I can state and apply Green's theorem right there. I've literally worked up my answer to be in terms of a boundary and a boundary circulation double integral of Green's operator over the interior. Okay, how are we doing? Is everybody okay with that first line? A lot of students will just go straight from there to there. I want to strongly advise against that. I emphasize this class is not about answers, it's about reasoning. And said differently, it's not sufficient to just have true statements on your page, right? What you need is true statements that clearly follow one from the other. There's actually 3 steps that go into what I have highlighted in green here. 3 important, significant ideas. There's a recognition of what happens in relation to switching orientation. This is an important concept. Right? It's a significant, meaningful, non-trivial concept. There's the very important fact that a curve is a boundary. Right? This recognizes that. Right? And then finally, there's the actual implementation of Green's theorem. So I strongly advise, right? Keep in mind that graders, be it me or a final exam grader, they likely won't be me, right? We'll be looking for clear evidence of understanding of the important ideas, and it doesn't take that long to a little doff with a cap to each of these 3 important ideas, and you will ensure you will increase your odds of not dissatisfying a picky grader, right? If you show all of the big ideas as I've done in this talk down here. Let me pause on that. Is everybody okay with that? Everybody see what I'm talking about? Feel free to ask. Okie dokie. It's all downhill from here at this point. We've got to compute Green's operator. How are we going to compute Green's operator? Well, we've got a formula, dq dx minus dp dy. The x partial of q is pretty clearly 3. Right? Then we have to subtract now minus the y partial of p, pretty clearly 1. And this is kind of beautiful, but the ugliest part of q disappeared in the partial derivative. Hey, isn't that lovely? Sometimes everything just comes together. It's really nice. Likewise, the ugliest part of p disappeared in the partial derivative. And what had been kind of a, not very pleasant looking vector field turns into, and again, a lucky break, and won't always be this nice, but it turns into a lovely Green's operator integrand for the double integral. And so you find yourself, therefore, with a really easy double integral to compute and nice punchline, easy answer. Everybody okay? All right. Okie dokie. Moving along. Another example. Here we have a curve that's made up of line segments that start at the origin. Then from the origin it goes to 2, 2, and then down to 2, 0, and then over to 0, 2, and then from there down to the origin. So this is, I think of this as being kind of a triangular figure 8 sort of deal. Right. Right. So there's our curve. And on that curve, I want to compute a line integral of this vector field, and off we go. And again, notice no indication in the statement of the question what tool to use. Right? The brute force approach to computing this would be to break this up into 4 separate integrals. And again, pretty undesirable. Even though the vector field's not that bad, right? We could do this. We could parameterize each of these 4 curves and deal with, it's just first order polynomial. It's not that bad, but you can see there's going to be a fair amount of simple tedium if we were to do that way. Okay, so I'm going to say that's an undesirable way of doing it. So here's the clever idea. We're going to look at our curve and ask ourselves, does this look like a boundary? And if it does look like a boundary, how can we make that precise? And then, once I have it written as boundary or boundaries, then we're in business. We can use Green's theorem. So the first observation I want to make is that I can break up the curve into pieces and then kind of recollect them as that blue curve plus this green curve. That's all the same pieces, just kind of chopped and sorted a little bit. And now let's look at these one at a time. What can I say about the blue curve? Well, the blue curve, happily, is exactly, wrong color. The blue curve is exactly the boundary of this region. Let's see here. What color am I going to use here? I'll use orange, I guess. It's exactly the boundary of that region D1. Lovely. Very convenient. Is everybody with me? Notice the orientations, correct and all. All good. Okay. Next, let's see here. Let me do this just to keep everything on board. Now let's look at what I have on the right here. It's tempting to say that this green curve is the boundary of this yellow region. But is it though? Right? We got to worry about orientations, and doggone it, the orientations are not going the correct way. So this green curve is not a boundary as written. Right? But here's the good news. Even though the orientations are not correct, all the way around this green curve, the orientations are exactly wrong. And that means that what we have here is just simply the negative. It's the opposite orientation of what is in fact actually a boundary, right? So this thing here with the minus sign to recognize the opposite orientation, right? With that minus sign to turn things around to this as they should be. This is the boundary of this yellow region D2. Is everybody with me? Okay. All right. So, cool. We have written our curve in terms of boundaries, and we're in business. This just is a recognition that the curve is the boundaries as stated up here. Then I am going to go ahead after that and deal with this opposite orientation issue on sort of the second half, if you will. The boundary of D2, of course, is oriented the wrong way, so I'm going to take that opposite orientation superscript, use that to justify putting this minus sign on the outside, and it's all over but the shouting at this point. So notice we have a circulation, boundary circulation, which I can rewrite with Green's theorem. Yeah.
And so the orientation is just determined from wanting to have the area on the left side.
Correct. That's when you say the word boundary, and you have to when you use Green's theorem, right? Green's theorem means you're talking about a boundary circulation, then exactly what you said, the orientation has to be, respecting the usual rule, regions on your left. And so, that's the goal. I put the minus sign on there so that I can make reference to an actual boundary properly understood with the proper orientation. Yep. Everybody else all right? Feel free. Okay, so Green's theorem. Circulation is a double integral. Green's theorem over here, circulation is a double integral. No problem because I've dealt with that opposite orientation issue. That minus sign has taken care of that worry for us. So simply two applications of Green's theorem. Green's operator in this case, very easy to compute. Let me zoom out so I can fit this all on. Green's operator applied to this vector field. dq dx is 5. dp dy is minus 4. So Green's operator is 9. And it's really all over but the shouting at that point with Green's operator being 9. Right, we have an integral of 9 on a couple of triangles. 9 is a constant. Therefore, you get 9 times the area for each one of them. And then you look back up to your picture and notice that these two areas are the same because of the, simple geometry of it all. So our answer is 0. Much simpler answer than actually brute force cranking out all 4 integrals. Yeah.
Can you say just without explaining?
Oh, you mean like a symmetry theorem? Yeah, no, definitely not. The reason why here is if you look at this vector field, it doesn't have any particularly obviously nice symmetries. Right? So if you want to say, the left half looks just like the right half, kind of sounds like you want to use a symmetry theorem, right? And symmetry theorems only work under very narrow specific conditions. So the fact that these two areas are the same does not mean that two integrals on them will always be the same, right? And this vector field that's just really not clear, odd or even or neither or what, is just it's really not clear by looking. And here's what's worse. In fact, there is no odd symmetry theorem or even symmetry theorem for vector line integrals. So that's yet another reason that we can't do that. Does that make sense? So very tempting, right? Totally get it. But, no good. So as much as I love symmetry, we do all have to be on the lookout for, make sure symmetry is a delicate, very narrow, very rigid tool. And you always got to check all the, dot your I's, cross your T's, etc. Yeah.
But if the integrand was any sort of constant, the integral would always evaluate to be 0, right?
Well, when you say the integrand, which integrand?
If it was like 9, let's say it was like 70 instead of like 9.
You're talking about down here?
Yeah.
Oh, well, now these integrals, you can make easy arguments down here because these are double integrals. They're not vector line integrals anymore.
But so once we get to that point, you'll get this.
Oh, yeah. Oh, absolutely. Here I wouldn't actually make a symmetry argument because this is two separate integrals. And if you were to try to write this as an integral it'd be more trouble than it's worth, basically, because you'd have to, it'd just be set up that you'd have to do, right? I think it's much easier to argue here that these areas are clearly equal. That's just geometry. And 9 times something minus 9 times the exact same thing. It's just easy that way. Yeah. Okay. All right. Moving along. So here's a quirky quirky little application that one can do. It's kind of unexpected where this comes from. First, let me write down in recognition of Green's theorem that here's where we use Green's theorem. I like to start with that. So what I'm about to show you is an application of Green's theorem, because that's where Green's theorem gets used right there. Notice I'm specifically applying Green's theorem, though, to this vector field 0, x. And why on earth would we be interested in applying Green's theorem to that one specific vector field? And the reason why is kind of beautiful how this works out, but Green's operator applied to that vector field is just 1. And that's awesome. The reason it's nice for Green's operator to be 1 is because then check out my integral. Now I've got an integral of 1, and of course that just gives me area. So what that means is, just because of the fact that we're applying Green's theorem to this special vector field, and it's not unique, but it is particularly convenient for this purpose, Green's operator is 1, which means Green's theorem is going to compute area for me. So what I've got then, connecting these dots together, is a line integral that will compute the area enclosed inside of it. And that's very strange, very unexpected. It's a very nice tool for computing areas. I'll show you an example in just a moment. Real quick, I do also want to point out that this is an alternative way to write it, and frankly a more common way to write it. And honestly, in this case, I think even arguably a better way to write it. And I know I did a bunch of trash talking last time about how coordinate line integrals are usually a clunky notation, right? But you can see in this case, I think it actually is a little more streamlined in this case. Right? Now, double check, make sure for yourself that you're very comfortable with how these two things are equal. Right? Keep in mind, when you have a coordinate line integral, you got to interpret it as such according to the rules and that what we discussed last time, and that you could reproduce that the vector field being referred to here, 0, x. If you have any trouble making that connection, come to office hours. I'm happy to explain. Ask a friend, help room, whatever. Okay, so how it usually gets written then is that integral x dy computes area. Ultimately, a consequence of Green's theorem. Now, you may be thinking to yourself, thanks but no thanks. Why do I want to deal with that? I'll just compute the area myself. Just directly, right? This seems like an easy high school geometry question. That seems like work. Right? So why would we ever think otherwise? And a couple of things. First of all, let's look at this example down here. And I know I just skipped something. I'm coming back to it. Sometimes area are a true pain to compute. Right? Like that shape right there. I don't even know what to call that. What a weird... It's a polygon, right? But this is a particularly weird shaped polygon. How would you compute that area? And you can chop it up into triangles. But those triangles are hard to compute the area for, because when you chop this up into triangles, for example, when you do like, let's see, when you do like that, oh come on, this, and then like that, and then maybe this, and that, and that. How many we got there? 1, 2, 3, 4, 5, 6. We got 7 separate triangles, and I don't think any of them are right triangles. Each one of these 7 triangles is going to be a real pain to compute the area of. And I don't know, maybe 1 or 2 of them are right triangles. Plenty of them are going to be a pain to compute the area of. So, highly undesirable to compute area that way by chopping into pieces. This is, in fact, a pretty nasty problem. Right? So, having the alternative of computing in a different way starting to seem maybe a little bit more appealing. And then here's the even better news. This integral, again, you can look at this integral and think, well, golly, that's a bunch of calculus, anti-derivatives I'm going to have to compute, and I'm going to have to parameterize something, etc. On a straight line segment, This only applies to straight line segments. On a straight line segment, the value of that line integral is a really simple formula. It's the average value of x times the change in y. Really simple. Again, only for straight line segments. But nevertheless, notice that that's what we have here. Right? Each one of the sides, each one of the segments, if you will, of the boundary of this horrifying shape is a straight line segment. And so on each one of these pieces, so this being, item, the edge 1, I can look at, what is the average value of x? Let's see here. Let me try to get all this on. The average value of x. I'm going to look at the two endpoints. Average those, right? 1 and 12 average to 13 halves. Right? Delta y, aka y2 minus y1, right, is 5. Easily computed there. Right? And therefore, on that edge, the value of the line integral that I'm computing there is just, it's just that product. And, a little fraction. Oh well. But still, boom, answer. Easily computed. And all you got to do is just keep going. Keep doing this on all of the edges. And okay, it's a lot of edges, and I grant you that, right? But it's really not that bad. Again, on this edge, we get that. Then on this edge, we get that. And then on this edge, oh, come on. That edge, we get this. Notice the minus sign. You have to be careful about this delta y. Delta y, let's go to the delta y is y2 minus y1. If the curve is pointed downward, that means that delta y will be negative, thus this minus sign, thus that minus sign. It's a heads up on that part. And just keep going around. And it's pretty straightforward, simple arithmetic, and boom, there's your area. This case happens to be 19. Right? Way easier than trying to take a high school geometry approach on this question. How we doing? Everybody okay? All right. So, nice little tool for the toolbox. Alrighty. Okay, so new topic. We'll talk about flux. We've already talked about flux. Flashback chapter 3. Remember we talked about what it means to... we started off with this physics question of if I have a fluid flowing and then I have a surface, and if the fluid is kind of flowing through the surface, and I want to keep track of how much, quantity in whatever sense of fluid is flowing through the surface per unit time, based on the velocity or whatever the vector field is that's representing that fluid flow. How do we compute that? And the answer was this thing called flux. It's F dot a normal vector times the area. And here we're going to ask a very similar question, which is we're going to look now at a two-dimensional fluid. It seems non-physical perhaps, but we've seen examples of two-dimensional fluids. Again, my favorite example is if you're looking at like a flock of birds, or what do they call it when you have a bunch of a herd, right? Like a herd of wildebeests or whatever, right? You can think of that grouping of animals as a kind of a fluid of sorts, right? And it's intrinsically kind of two-dimensional in terms of keeping track of where they are on the two-dimensional surface of the Earth. Anyway, two-dimensional fluid of whatever sort. The natural extension of talking about fluid flowing through a surface would be fluid flowing through a curve. Let's say in this case, a line. And I'm going to leave the details as an exercise, but they're extremely analogous to what we saw in Chapter 3. So this would be a nice practice problem. Notice this is kind of this is not asking you to extend to a higher dimension. This is asking you to reduce to a lower dimension? Right? This is an easier question than what we did in chapter 3. But you get this highly analogous result that flux, quantity of fluid per unit time is F dot N times the length of the piece of curve. All right. Again, good practice problem. Give it a shot. If you get stuck, come talk to me in office hours. Very happy to help you fill in blanks there. Okay. So now, related idea, I want to talk about this thing called boundary flux. Boundary flux is flux. It's exactly the same thing. Just with the understanding, and again, anytime you hear this word boundary, right, this is a new loaded word. Boundary now specifically refers to an orientation, a specific conventional orientation. And again, this could have been done either way 150 years ago at some point in the distant past, but convention got chosen. There is a standard. It is worldwide, and we're going to stick with that. The word boundary in this case means outward. Flux outward through the boundary of whatever region you're looking at. Arbitrary, but standard. Okay. So, yeah. Real quick, why would we be interested in the flow rate across a boundary? If you think about it, flow across a boundary represents fluid leaving your region. So if you're interested in how much fluid you have in a region, pretty naturally you're interested in the rate at which the fluid is leaving the region. So boundary flux is actually a pretty natural thing to want to talk about. It helps you keep track of how much fluid you've got in your region by keeping track of how fast it's leaving. Everybody on board? Does that seem plausible? Yeah.
How do we make a normal vector to the boundary there? Because won't at any point on the boundary we have a different normal vector?
Absolutely. Yep, we're going to factor that in just a minute. Yeah, it's kind of like with tangent vectors, though. So if you think about, if I give you some non-straight curve, when you parameterize that curve, the tangent vector is going to be different everywhere. And so there's a formula for it, right? It depends on where you are, but yeah, there'll just be a different formula. Yeah. Anybody else? Okay. Right, so this calculation I'm about to show you is going to seem unclear why we're interested in this, but I think it's ultimately a pretty natural pitch. So anyway, for the moment, just bear with me and just don't worry about why we're interested in this. If I want to know what the dot product is of a vector field with a normal vector, let's think about how we compute a dot product. Different formulas, multiply the coordinates and all that stuff. But another way to compute the dot product, I can look at the magnitudes of these two vectors. I can look at the angle between them, and product of the magnitudes times the cosine of the angle, old formula for how to compute a dot product. Next observation I want to make is that if you rotate 90 degrees counterclockwise, none of that changes. Right? If you rotate both of these vectors 90 degrees counterclockwise, the angle between them stays the same because they both got rotated by the same amount. Furthermore, when you rotate vectors, magnitudes don't change at all. Right? So I can talk about taking both of these vectors, F and N, and what happens when I rotate them both counterclockwise. And here's what we get, by the way, when we rotate them both counterclockwise. I have a simple formula. I don't know why I can't draw a straight line today. I have a simple formula for how to rotate counterclockwise. That's an old Math 218 thing. Again, if you're if you're a little shaky, a little uncomfortable with that 90 degree counterclockwise rotation, that gives me negative Q comma P. Come to office hours, we'll straighten that all out. Old Math 218 linear algebra trick there. And then I appeal to your geometric intuition. And let me momentarily delete everything else just to get it out of my way. If you rotate a normal vector, the result is a tangent vector. And more specifically, if you rotate an outward-oriented normal vector 90 degrees counterclockwise, you will get a, how are we going to say this? Well, you'll get a tangent vector, but where the region's on your left. So said differently, when you rotate the correctly oriented normal vector, the result is the correctly oriented tangent vector. Just a little fact of geometry, as it turns out. Oh, and then let's see here. Let's see if I can get all this back. I don't really need it. So, punchline of all of this dot product, F dot N, is the same as this dot product, F perp dot T. So the green dot product equals the blue dot product. Is everybody with me? Now I'm just going to set that aside for the moment. Now let's get to actually computing a boundary flux. Here we go. If I want to compute a total flux, I'm going to chop my curve up into a bunch of little pieces. Right? I can look on each piece. On any given little piece here, let's take this piece right there. On that little piece, there's going to be a certain amount of flux, and then I just add that up over the entire curve to give me the total. Then I can make the case that I already know how to compute flux on each little piece. On each little piece, it's approximately straight. The normal vector's therefore approximately constant. The vector field, it's a little piece. Vector field's approximately constant. And I just use this formula up here. So I have F dot N times length. Length big do S, of course. And here's where we use this result over here. Knowing that F dot N is equal to F perp dot T allows me to rewrite this as that, which allows me to take an integral that I don't know how to compute. Right? We've never seen this before. Integral of something dot n ds. We don't have formulas for that. We've never seen it before. We don't have any tools for computing it. Right? This is kind of a dead end. We turn that now into this, which is extremely familiar. The 2dx. That's just dx. And integral of vector field dot dx, old news. We have multiple tools for dealing with that. So that's why we cared about this little rotation trick. It's a clever move. And that gets me down to a regular old vector line integral, to which I can apply Green's theorem. Green's theorem is just about computing an operator. So Green's operator, this right here. Gotta be careful when you compute Green's operator here. Let me give a little bit of a discussion to this. Green's operator. Keep in mind, what Green's operator does is it takes the x partial of the second component, but be careful, my second component now is p. X partial of my second component, and then minus the y partial of my first component. And again, be careful. Oh man, I missed. Okay, the first component is minus q. All right, so you gotta always be careful when you're, remembering formulas for things like Green's operator or whatever else. It's not about the letters; it's about the role that they're playing in the situation. So we memorize Green's operator as dq dx minus dp dy, but that's if you're applying it to the vector field p comma q. It's really x partial of the second component minus y partial of the first component. And in this case, that gives us this, which, of course, we can rewrite. Right, minus of a minus is a plus. Oh my gosh, we recognize this expression. That happens to be exactly divergence. which comes out of nowhere seemingly, and a nice punchline then, flux. Boundary flux is a double integral of the interior of the divergence. How we doing? Is everybody on board? Everybody follow those? There's a bunch of little steps in there, little micro annoyances. Yeah.
Do we need to prove this every time?
No. You can this is now proved, and you can use this unless the question is to demonstrate where this comes from. Yeah, this is established, and if the question says compute outward-oriented boundary flux, bang, straight to that. Totally fine. Exactly. All right, so a couple of things I want to say this. You'll notice I have this labeled here as the two-dimensional divergence theorem. We have not gotten to the three-dimensional divergence theorem yet. We will. Right? That'll come in chapter 7. The three-dimensional version is the more common. It's the more physically powerful. It comes up in a lot of areas. It's a big player in electricity and magnetism and gravity and understanding gravitational fields and stuff like that. It's a really big deal. The two-dimensional version here is less so because we don't live in a two-dimensional world, but nevertheless, it's morally the same theorem. So what you're going to notice when we get to chapter 7 and develop our three-dimensional divergent theorem is the results a lot like this. It really does look very similar. Very, very similar. So you can think of this result then as being a variation on a bigger theorem to come, Gauss's divergence theorem. But notice also, the thing that made it all work, the thing that did all the heavy lifting, was Green's theorem. So you can also think of this instead as being just a twist on Green's theorem. And I think that's also a really valuable point of view. After all, this is a two-dimensional theorem, and Green's theorem is a two-dimensional theorem. So, either way is fine. Example. We've been asked to compute flux. Okay. We've got a vector field given. We have a curve given. Notice even with an orientation, specifically outward through the circle. Okay. And we want to compute this flux. Notice, very importantly, this curve, nowhere in the statement of the question does it say boundary. So we have to make the insight. We have to be sort of like on our toes, ready to check. Whenever someone asks us to compute any of these kinds of oriented integrals, we have to be on our toes, ready to ask, wait a minute, is it a boundary? Is this a boundary? Is this oriented the way it's supposed to be? And if so, then you've got a way that you can solve the problem. And in this case, unit circle, yes, that is a boundary. Is it oriented the way it should be? Why, yes, it is. Outward. When you're computing flux, outward oriented is correctly oriented. That's what the word boundary means in this context. So, the flux in question, double integral of divergence. Divergence is easy. The x partial of that gives me 2. The y partial of this gives me -5. And so a potentially really hard flux line integral turns into a really easy double integral, and we win. Everybody good? Okay, last couple things I want to say here are just kind of observations. I said at the start of class, and I said it last time as well, accumulation theorems, well, let me say it differently. If you have any sort of accumulating quantity, that's a big tent, right? Mass, population, work, countless other examples, and now also circulation. Then you can make a corresponding theorem. And so looking at circulation as an accumulating quantity led to Green's theorem. Nice. Well, here's the clever move. Boundary flux is also an accumulating quantity. the whole is the sum of the parts. And it doesn't feel like it would be, because when you're looking at the whole, outward-oriented boundary flux only happens on, well, in fact, the outside, what the boundary, where the boundary is. When you cut it into pieces, you're creating new pieces of boundary, and that's going to create new flux terms, and you feel like, well, we're making new perimeter here, basically, and fluxes are computed on the perimeter, and it doesn't seem like it's going to work out. But as part of the boundary of this outward, aka the outward-oriented boundary orientation, is to the right. Thought of as part of the boundary of this outward is that way. And when you add them, just like in this case of circulation, they cancel, because same curve, exact opposite orientations, minus sign, and then therefore they cancel. So, in fact, you can develop, and this is another lovely exercise, think it through, give it a chance if you're so inclined. You can make an accumulation argument, just like we did to get Green's theorem, for flux, and you will get exactly this result here. You will get the 2D divergence theorem. Okay, see y'all on Monday. Y'all have a great weekend. Have a good one. Don't forget to stick around for just a moment if I haven't already